You got it? Okay, can you see this? Okay, it is not there. Let me change the viewing option. Because if we do not use individual window, then it will be a big problem for us to show. Okay, now it is visible to you, I hope. Respond, please. Can you see it?
Yes, sir.
Yes, guys,
Yes, sir.
can you see it?
Yes, sir.
Yes, sir.
Yes, sir. I can
No,
see it.
sir.
Okay, then you try to understand the problem. Okay, this is a problem from your Sadiko's book, actually, very simple. You see that the problem description is what? At time t equal to 0, switch is opened. Before opening the switch, your switch was closed for the long time, and your circuit contains an inductor, and it was at a steady state, isn't it?
Yes, Yes, sir.
Later, your circuit is open, switch is opened at t equal to 0, and you have been asked to calculate the current flowing through the inductor IT for time t is greater than 0. This is what your problem. Now our strategy should be what? We have to consider two states. One that is time less than 0. Another state is time greater than equal to 0. Why we are needing time less than 0? Because whenever we are finding some differential equations for the current IT to be determined, we'll need the initial value, isn't it?
Yes, sir. Yes, sir.
Yes, sir.
That initial value will be coming from this state. Now you see that when your time was t less than 0, switch was closed, the circuit was a steady state. Then your inductance, as your source is a DC current source, your inductance will be behaving like a short circuit, isn't it?
Yes, sir.
And you see that the part of the network actually comprises a delta.
Yes, sir.
You can convert it into Y very simply. Then your network will be looking like this. What is the thing that you need to determine? You need to determine current flowing through your inductor I. We are calling it I0 minus. Then how can you do that? Just you simply use the current divided rule there twice. First thing is that you have to find your I1. In that case, you have to just replace this part of your network by an equivalent resistance. Then once your I1 is available, then you again divide it into two parts. One is flowing through this resistance. In that branch, your inductance is there, isn't it? Behaving like a short circuit. You got the point?
Yes, sir.
Then your current will be I1 will be equal to it must be ampere, 12.5 ampere. Okay. Then let us go to the next page.
Yes, sir.
So you see that in your next page, you can easily find that what is the current flowing through your inductance. Then your IL0 would be equal to 5 ampere. Okay, you can easily verify. Now the question comes that once that current is available to us, this is what our IL0. Next thing is what? Next thing is you have to deal with your circuit for time t is greater than 0, isn't it?
Yes, sir. Greater than 0.
Hey, respond.
Yes, sir.
Respond na korle class niye moja pawa jay na. You have to be very careful about it. Okay, this is actually time.
Sir, we are responding,
okay?
sir.
You sir. Oh, delay.
Yes, sir. There is a delay, sir.
Okay, because the network
Yes, sir.
is
It's
here
for the
in
delay, sir. We are
IIT,
responding.
I cannot find. Okay, no problem. Inshallah. So this is what your network, isn't it? After opening the switch,
Yes, sir.
Hey,
Yes,
if
sir.
you open your switch,
Yes, sir.
if you open your switch, will there be any source in your network?
No, sir.
Because
No,
that
sir.
current source will be disconnected. Disconnected. As a result, your network will be looking like network will be, you will be seeing your network something like this. Okay. This part of the network becomes here important. Okay. So now the thing is that that network doesn't contain any source, but it will have two resistance there, 60 divided by 25 equal to 2.4 ohm. Another branch will be 1.6 ohm, and inductor 2 Henry is there. That inductor is carrying an initial current equal to 5 ampere, isn't it? So
Yes,
if
sir.
we just derive the differential
Yes, sir.
equation across by applying your Kirchhoff's voltage law across this loop, this would be your differential equation. Okay, you verify it. Now you can you imagine that this is your first order differential equation, isn't it?
Yes, sir.
What will be
Yes,
the
sir, first order.
analytic solution? Analytic solution I t would be equal to simply I0 minus e to the power minus 2t for time t is greater than 0. This is what the analytical solution. Here your I0 minus equal to 5 ampere. This would be your current then. Okay, so this is the analytical solution. You can easily determine. Our objective is not something like this. We will need this in some problem in order to calculate how much error will be incurred in applying our what numerical technique. Okay, let us now apply numerical technique. Okay, you see that analytical solution already we have. And if you want to solve it by using numerical method, then you can, how many numerical method you need to know? You know, we have our at least
Euler method,
3 or
Lewis
4
method,
numerical
Parker
methods
method.
with us. Then any one of the numerical method can be applied just to solve this problem. Okay. Okay, you can use Euler method. Here you see that, yeah. Here you see that this is what your equation you can rewrite. And this is the slope of your current. Okay. Our Euler method says that in the next time step current I plus 1 would be equal to II plus calculation of your slope at I point multiplied by a step size. We are considering a step of say 0.01 second. If this is what current at 0 plus slope multiplied by what? The step size.
Yes, sir. Yes.
So you see that our slope was equal to 2 into II.
Yes.
Actually, for your first step 2, this is your I0 multiplied by step size 0.5. And your current is equal to 4 ampere, isn't it?
Yes, sir.
Yes,
So
sir.
your numerical method, initially current
Yes,
was
sir.
5 ampere. In the analytical case, it was also 5 ampere. Now in time step 1, your current is 4 ampere. And then if we put 0.1 in our analytical equation 5 e to the power minus 2t, then we will obtain 4.09. So this you can easily calculate what is the difference or error at this time step. Okay, fine. Then our point is at 0.1 second, our current is known to us equal to 4 ampere. And we go to our next time step. In our next time step, just hold a second. A call came from the vice chancellor. Okay. Hello, assalamu alaikum. Hello, can you hear me? Yes,
Yes,
boys,
sir.
can you
Yes,
hear me?
sir.
So we can hear you, sir. Are you speaking to us?
So using this
Yes,
time
sir, we
step, we
can.
can calculate the current for. Sorry.
Sir, we are
Then if you want to calculate the current for your second time step, that will be equal to current. What? I cannot follow you. Please repeat.
Sir, actually, when we are talking, you are getting the response
sir,
after
what,
like 2 or 3
we
seconds,
are
sir.
talking about.
That
We
is
can hear you.
why our
Are you there?
answer is not synchronized, sir.
Then how can I get rid of it? I have to speak slowly.
Yes, sir. You are getting the response after a
So
few
you
seconds,
got
sir.
this point. That for
Yes, sir.
current at 0.2 second. But few means a bit very longer, I think. Okay, it didn't happen earlier. Okay, I hope you understand algorithm. You can proceed with calculating for other steps. Then you can compare the result with the analytical one and can calculate the absolute error also. Okay.
Yes, sir.
I will upload these slides to you Google Drive. Okay.
Yes, sir.
Or share it with
Sir.
you. Now we have another
sir.
problem.
Sir, sir, can you
This
share me
problem
one
is
problem?
reversed.
Sir, in partial differential equation,
please.
yes, sir. In partial differential equation, there was irregular boundary from the book. I have studied the proof of the. I've studied the proof of the equation, but I couldn't make sense
We
of
are
it.
not discussing about. Okay. We don't need to, what are we discussing now? We are discussing about OD. Okay, later classes will be on PD at time you ask this question. Okay.
Okay, sir. Actually, we had a quiz today, sir. Okay, sir.
Sorry, I cannot follow you actually. My strategy is what? We are starting with OD. We will gradually go to PD. At that time,
Yes,
you
sir. Yes,
can
sir.
ask you a question. I cannot address this thing here while I am doing with OD. The boundary is there. It is not very difficult to be understood. We will do that.
Sir.
Okay.
He was trying
This is your another problem. Why do you see that you switch your
Sir.
what? Very disturbing. I cannot continue this class probably. Should I postpone the class for today?
Sir, I think if you reconnect your network, then things might actually improve.
Very difficult. I have already reconnected and it is there at I am at IoT. I am using IoT Wi-Fi. And it is the signal strength is
It's quite hard for me to follow you like this.
Is it okay now?
Yes, sir, we can hear you, sir.
Okay, let us postpone our lecture today. We'll continue tomorrow, okay?
Okay, sir.
But if some students has problem, then I cannot, how can I proceed then? Okay, should I continue then? Okay. So this is your problem. When the t equal to 0, your switch is closed, and before that, switch was opened, isn't it? Then you have been asked to calculate the voltage across the capacitor per time t is greater than 0. This is what your problem. In this case, you have to analyze your network per time t is less than 0. In this case, you see it was at a steady state capacitor was open someplace. Then you can find the open circuit voltage that is equal to 15 volt. That is what the initial value of capacitor. Later, what you can do? You just open your capacitor from this branch and replace the network with Thevenin equivalent, and you place your network in a way of a first order. Your network will be something like this: VTH, a Thevenin resistance will be there, RTS, and you insert your capacitor there 1/3. Then it will give you a first order differential equation. Your initial value is there. You can apply any numeric method to solve them. Okay, this is what the solution with you. Probably you know the solution from your very basic circuit, the analytical one. You see your analytical solution is equal to what? For this type of circuit, it is V infinity minus plus V0 minus V infinity per T divided by RC. So your analytical solution for your current is there. Actually, this is IT. So your analytical solution is there. This is your differential equation that relate your capacitor voltage with your Thevenin voltage. Then it is a first order differential equation. You can proceed with solving by using Euler technique or Runge-Kutta or whatever it may be. Okay, this is what the solution I have shown by using Euler. This is what is equation. And if we represent with our Thevenin voltage was equal to 9.375 volts, and then this is what your equation, and this is the slope. Then this is the algorithm that your next time step voltage is equal to previous time step voltage multiplied by slope with your step size. If we consider the same step size 0.1 second, or you can choose an appropriate step size, you can find your voltage at the capacitor at 0.1 equal to 13.875 volt. The analytical is shown in the blue text, and in 0.2 second your voltage is there and the analytical solution is there, and for 0.3 second your voltage is there, the analytical solution is there. In this way you can have your solution done. And in the case of your first example, no source was there. But in this example, you have your source already there in your system, and eventually it will reach at a steady state, and your capacitor will be fully charged with your Thevenin voltage VTH. This is an example of operational amplifier from your book. Can you see this?
Yes, sir.
Yes, sir.
Yes, ， sir.
， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, sir. ， Yes, s
Okay, in which mode that operational amplifier is actually working?
Sir, differentiator.
Is it not a non-inverting amplifier? In the non-inverting mode? Okay. Now you see that if your switch was open, no source was there, so your desired output is the voltage across your capacitor V. So if we don't have, for example, our switch was open for time t is less than 0, no voltage was there, as a result, your capacitor voltage is 0, that this is what the initial value. Next step is what we have to derive the differential equation that will relate your quantities. Now, when switch is closed and your operational amplifier is ideal, then no current is flowing through the positive terminal, it is virtually open. Then your V1 voltage can easily be determined and it will be remaining constant and can be determined by potential divide rule. Your V1 would be equal to 3 divided by 30 kilo ohm multiplied by 20 kilo ohm equal to 2 volts. So this is what the voltage at V1. So when that voltage is at V1, then voltage at the plus terminal will also V1 minus terminal is also V1. Voltage at the node 1 would be equal to V1. If your node voltage 1 equal to V1, then this voltage is equal to V, then you can easily say that your V would be equal to V1 minus V0 because this node voltage is the output voltage. Now, if you want to find the differential equation, you see that we can apply our KCL at that node. You see that at that node, you have a current there going through this resistance. You have a current going through the capacitance, and you have a current leaving this node 1 to the ground. Then can we write our Kirchhoff's current law at node 1?
Yes, sir.
This is the current flowing through your capacitor going out of node. This is the voltage current flowing through your 50K resistance. It is also going away from the node. And this is what the current V1 divided by 20K. This is also going away from the node. So this is what you differential your nodal equation there. Then if we rearrange them, so calculate them, we will be obtaining a differential equation of this form. Is it not a first order differential equation?
Yes, sir.
And you
Yes,
can
sir.
solve it by using any one of the numerical technique, try to solve it. Allahu Akbar. Okay, please note this example very carefully. In this example, what is the difference between the earlier example and this example?
So there's a current source and dependent current source.
And what type of current source is it?
Sir, current dependent current source.
So it is being just similar statement is that if we have our switch closed for a long time and at time t yes, exactly, very good. So when our switch is opened at time t equal to 0, then you have to find the current I for time t is greater than 0. Our first thing is what we have to find, because that current I after closing opening the switch will follow a differential equation because we have a capacitor there. So in order to solve that differential equation, we will need initial value. and that initial value comes from the circuit T is less than 0. So you see that it is a DC circuit, and for time T is less than 0, your capacitor is fully charged and it will be having one open state, and your network is drawn there for time T is less than 0. Then you can apply your capacity, because our objective is what we have to find the capacitor voltage, and that voltage will help us to find the current I. So 50 ohm resistance, I combined 50 and 30 ohm resistance to 80 ohm because they are in series. And you see that your current dependent source is depending on the current that is flowing through 50 ohm resistance, I. Then you can apply your node Kirchhoff's current law at this node. Then you see that current leaving the node equal to V0 minus 80 divided by 40 ohm. And current leaving the node another branch current leaving the node through 80 ohm is equal to V0 by 80. And that is equal to current entering the node equal to 0.5 I. And you know that your I equal to V0 divided by 80, isn't it?
Yes, sir.
This is what your I. That if we replace our I, this is the equation. Solve this equation for V0. Our V0 would be equal to 64 volts. So once our V0 is available, I0 is calculated equal to 0.8 ampere. This is what the initial current flowing through our resistance for time T is less than 0. So our initial current is determined. Now we are opening the switch at time T equal to 0. For time T is greater than 0, this is what your network, isn't it? Then you can easily apply your, we have to derive the differential equation. Two ways can be there. Either you can find the Thevenin equivalent or you can directly write, okay? I am directly writing. You see, if this node voltage is V, and that voltage is equal to what? The current I is flowing through 80 ohm resistance. Then if not that V equal to 80 I. This one, please. This current is I, this node voltage is V. Then V equal to 80 I. Is it okay?
Yes, sir.
হ্যালো, আমি ক্লাস নিচ্ছি এখন, কি অবস্থা বলেন
Yes,
তো?
sir.
ক্লাসের মধ্যে আছি এখন, তো অনলাইনে ক্লাস। কি ব্যাপারে, কি ব্যাপারে? হ্যাঁ হ্যাঁ, কথা হয়েছে, কথা হয়েছে। হ্যালো, okay. Then can we write our equation now? Again, you write your Kirchhoff's current law in this node. Then your current leaving this node equal to what? It is the current flowing through your capacitor. Your capacitor is D. Is it not equal to 3 dV by dt?
Yes, sir.
Yes. And current entered, the current leaving another node through this node is equal to I. And current entering the node is equal to 0.5 I. Then by using this equation, V equal to 80 I, our objective is what? We have to find I. Then we have to replace our V by I. Then this is equal to what? It is a very simple equation. This would be the equation. Then you replace your I by using this equation. You will be obtaining a differential equation. then you solve it by using that equation will be this equation, okay? Di by dt plus I divided by 480 equal to 0. You can easily choose an appropriate time step, then proceed with your solution. Analytical solution would be equal to I e to the power minus t divided by 480 t. Okay, these are the actually problems I have so far made for you. Now we can illustrate a second order problem. Then I will finish my review. I hope you have the books with you, circuit books. Can you see the whiteboard?
Yes, sir.
Yes, sir.
Okay, this is a problem from your Alexander Sadiq's book. Okay, your circuit is something like this. That at time t equal to 0, it was transferred to this position. Okay, say this position is 1, this is 2. At time t equal to 0, your switch is placed here at 2. And before that, your switch was connected, for example, with this circuit. Your switch was something like this, okay? And your circuit was at a steady state. Oh, a resistance is there. Eight ohm. Now tell me, when you for time t is less than 0, what was the situation?
Sir, the inductor and capacitors are fully charged.
Is it not the circuit, for example, for time t is less than 0? Yes, please.
Yes, sir.
Inductor is short circuited and a capacitor is open
Open circuit.
circuited, okay? So can you find your current, because your current I flowing through your inductor, let us consider this current is equal to IL0. What is the current IL0? Is it not equal to 30 divided by 10 equal
3
to
ampere.
3 ampere? Is it? And your V00 equal to what? Voltage across the capacitor. Is it not 30 multiplied by 8 divided by 10
Yes, sir.
by using simple potential divide rule? Is equal to what? 24 volts. Isn't it?
Yes, sir.
So your initial values are with you. But the initial value of this current equal to what? I00, it would be equal to 0 because this current is going through a capacitor and it is open circuit. So your initial values are already with you. Next thing is what? Let us draw our circuit for time t is greater than 0. At time t equal to 0, your switch was closed. And then your circuit is something like this. Is it not the circuit after closing the switch at time
Yes,
t
sir.
equal to 0? Now you see, is it not a, for example, very simple thing that it is what? It is a parallel circuit, isn't it? Parallel RC circuit, RLC circuit, isn't it?
Yes, sir.
If it is a parallel RLC circuit, then can we write, for example, the equation that will relate to V0T? How can I do that? This current was equal to what? I0 T. Then your V0T equal to what? Your V0T would be equal to, no, your I0T would be equal to what?
Sir, C
Is it not
into
C
dV0 by dt.
dV0 by dt? Isn't that something like this? Here you see equal to 1 by 4 farad dV0 divided by dt, isn't it?
Yes, sir.
Then your current flowing through your inductor, resistance this is IR. Your IR equal to what? Is it not V0 divided by 8?
Yes, sir.
Fine. Then what is the current then flowing through this inductor? If it is your IL, then equal to what? Your IL is equal to minus IR minus I0, isn't it? I0T, isn't it?
Yes, sir.
Okay. Then voltage across the inductor VL equal to what? Your VL is equal to V0 is equal to what?
Sir, L into
L
dV.
di L divided by dt, isn't it?
Yes, sir.
Then our L is equal to what? Di by dt. IL equal to what? Minus IR means V0 divided by 8. Minus I0 means minus 1 divided by 4 dV0 divided by dt. Is it okay?
Yes, sir.
Boys, students, is it okay?
Yes, sir.
Yes, sir. Understood it.
Then your equation is transferred into a form. Your equation is transferred into what form? Your L equal to 1 Henry. So this will be equal to minus 1 by 8 dV0 by dt minus 1 divided by 4 d2 V0 divided by dt2 is equal to V0, isn't it?
Yes, sir.
Or you can rewrite the equation in this way.
Yes, sir.
That 1 by 4 d2 V0 by dt2 plus 1 by 8 dV0 divided by dt plus V0 equal to 0. Or you can again write it in this way, dV0, d2V0, dt2 plus, how to do that? If we multiply it by 1 by 4, then it will be equal to half dV0 by dt plus 4V0 equal to 0, isn't it?
Yes, sir.
So this is a second order ODE. If it is a second order ODE, then you convert into two first order ODE. Then try to solve it by using any one of the technique, okay? And you can analytically solve it so easily because your two initial conditions are there. If you want to analytically solve it, what will be our solution? You see that your equation equal to d2V0 dt2 plus half dV0 by dt plus 4V0 equal to 0. What will be the characteristic equation? Is it not lambda square plus half lambda plus 4 equal to 0?
Yes, sir.
Then you can have your 2 lambda, lambda 1 and lambda 2 equal to what? Minus b minus 0.5 plus minus a square root of b square. B square equal to what? Minus 0.25 minus 4ac equal to 16 divided by 2. Is it not the solution?
Yes,
Lambda 1, lambda 2. Then your V0 would be equal to some constant a into e to the power lambda 1t plus b into e to the power lambda 2t. You have to find a and b. You put your initial value there because your V0 was known to you. V0 was equal to how many volt? 24 volt. It is known
24
to you.
volts.
Put time t equal to 0 there, 24 volt. Now, your current I0 was given equal to 0 ampere. If we know the V0, then I0 equal to what? I0 equal to C into dV0 divided by dt, isn't it?
Yes, sir.
And your C value was given equal to 1 by 4 dV0 divided by dt. That means you simply differentiate this equation, multiply it by 1 by 4 and put time t equal to 0 and equate it equal to 0. Then you will have two equations there to find your A and B. This is the analytical solution. But if you want to go to our what solution? Numerical solution, then second order equation cannot be handled so easily. What you need to do, you have to convert the equation into two first order equations, isn't it?
Yes, sir.
That conversion can be possible in this way that we have our one equation already known that I0 equal to 1 by 4 dv0 divided by dt. Then can't we write this equation in this way? That di0, okay, or dv0 divided by dt equal to 4i0. Then can't we write this equation in this way? 4 into di0 divided by dt plus 1 divided by 4 in half into 4i0 plus 4v0 equal to 0. Then you will have two equations there. One is di0 divided by dt would be equal to minus 1 divided by 4 into 2i0 plus 4v0. This is one equation. Another equation is dv0 divided by dt is equal to 4i0. Is it not a simultaneous equation to first order?
Yes.
And I hope that I have illustrated this thing earlier by using an RLC circuit to you during my lecture. Okay, so in this way we can handle a second order system and can apply our algorithm there. So let me finish my lecture at this point because I have to go to the Vice Chancellor's office. And the next day we will be discussing, inshallah, with partial and other examples. Time permits. You have your classes today at 7:30.